and it's calibrated every 1/10 of a milliliter. So if I read between the lines, I could probably read every 5/100ths of a milliliter. What the burette is used for, I put in the burette some household ammonia, which I do not know the molarity of. But we learned in chapter 4 that if you have a solution, say, of known concentration, which I do right here, this is exactly 1.0 molar hydrochloric acid. So I know its concentration. So I've got this setup here with the burette with the ammonia in it, which acts as a base, as you know, or maybe you don't know. Ammonia, household ammonia, is a solution of a little bit of ammonia in water so that it gives rise to a little bit of ammonium hydroxide in equilibrium with ammonia and water. But there is some of this in equilibrium. And it acts as a base. And what I'm going to do is I'm going to take it and I'm going to react it with this known molarity hydrochloric acid. I'm going to react it with 1.0 molar HCl. Oh, these are all aqueous solutions, of course. And when I add them in a 1-to-1 molar ratio, if I add exactly right, then the acid will neutralize the base and form ammonium chloride as the salt that's formed, and water is the byproduct that's formed. So they react in a 1-to-1 molar ratio. This is the balanced chemical equation for what goes on. So, and if I put the hydrochloric acid of known molarity, if I measure out a known volume, you remember molarity times volume is millimoles. And so I have this pipette, called a Pipet, and it's calibrated. It has a little marking right there that if I draw up that much of that HCl, I will have picked exactly 20 milliliters of that HCl. So I'm going to use the pipette, and I'm going to use this rubber bulb. I could use my mouth, and I have done all my life, but if I suck up too much, I'll get it in my mouth, which would be sour. Because acid is in fact sour. So I'm going to use a suction bulb to pull up the HCl. It's a safer way to do it anyway. And now, I do know the molarity of this. And, well, before I get started, since these things react at a 1-to-1 molar ratio, if I take, I'm going to take exactly 20 milliliters of this stuff with my pipette. And so if I start adding the ammonium hydroxide, which is a base, from this burette, and I'll add it and add it and add it and add it, if I first put in a little indicator, this is called phenolphthalein. Remember that word? It's a big old long word. I use the indicator phenolphthalein. That middle pH is totally silent. Silent, I meant to say. That's pronounced phenolphthalein. And phenolphthalein is colorless in acid. But in the slight excess of base, it turns a hot pink color. So, in this, when I set up my burette, I filled it with this household ammonia and got it exactly on the 0 milliliter mark so that I can tell how much I start to add. And when I was doing that, I drained a little bit of the ammonia out. So I'm going to show you that when there's ammonia and not acid, see, out of the bottle it's colorless. And it also stays colorless in acid. But look what happens in a base. You see, it turns that very hot pink color. So what I'll be doing is this. I'm going to take exactly 20 milliliters of the 1 molar hydrochloric acid solution, put it in this flask, this is called a flask, And then I'm going to add a drop or two of phenolphthalein. And in acid, it'll stay colorless. Then I'm going to put the flask under the burette and start adding ammonia. And as I add the ammonia, it's going to start by this reaction to neutralize the acid. So, and they're reacting at 1-to-1 molar ratio. So, if I measured out 20 milliliters of 1 molar HCl, well then I have measured out exactly 20 millimoles. So now, as I start adding ammonia, when I get to the point where I've added exactly 20 millimoles of ammonia, then it will have neutralized all of the acid, and the next little drop of ammonia will turn the phenolphthalein pink. And then it's when I'll know to stop my titration, because it comes out like a light. Now, as I start adding the ammonia, you'll see when the solutions mix, the stream of titrants, the thing that's in here, will turn a little bit pink, but as I swirl the flask, it'll start disappearing as it neutralizes. And only, see, I will stop my titration at the very end will be, it's called the end point, when I get my first permanent pink color. When the first permanent pink color stays, then I'll know that my titration is over with. And then I'll know, because these react in a 1-to-1 molar ratio, then at the endpoint, the molarity of the acid times the volume of the acid will equal the molarity of the base times the volume of the base. So I know this molarity because I've got it in a bottle and it's labeled exactly 1 molar. And I know how much I measured out. I'm going to measure out exactly 20 milliliters with my pipette. Now, I can find the molarity of the base when I read, this will be my burette reading. When I reach the endpoint, that is, I get my first permanent pink color, I will know that I have neutralized all the acid. Then you see, by doing a little calculation, I'll get this burette reading, and I'll put it in here, and then by dividing both sides by that burette reading, I can find the molarity of that base, having known the molarity of the acid I titrated it again, just by, you know. Well, actually, our ultimate purpose today is to do an acid-base titration, first finding the molarity of ammonia, because I'm titrating against a known molarity acid, and then I'm going to turn around and titrate that same ammonia versus household vinegar, which supposedly contains acetic acid, and according to the label, it says it should be 5% acidity. And so my purpose today is to prove the truth in labeling. I want to see if this is a true label that this is in fact 5% acid. It says it is, and we're going to prove it. Because we're going to turn around, after we know the molarity of our household ammonia, we're going to turn around and titrate that against, using a clean pipette, 20 milliliters of this vinegar, which contains acetic acid, and then we'll be able to find its molarity, and then by making an assumption that the density of this dilute solution is about 1, the same as the density of water, we'll be able to change molarity to percent and see if it truly is 5%. It doesn't say 5.00%, it just says 5%, so it's only one significant figure. So if we got 4.99, that'd be 5, isn't it? So we're just going to see. Because what I'm going to do next, after I do this titration is used to find the concentration of the household ammonia. Then I'm going to use that same household ammonia and titrate it against the acid in vinegar, which is this acid called acetic acid. can't tell you how many times this comes back in the write-up, written as if that's the adjective acidic. It's not acidic acid, it's acetic acid. And its salts are acetates. Okay, so when these also react in a 1-to-1 molar ratio, it turns out. And so at the end of the titration, I will have turned that into ammonium acetate. And of course water. And like I say, because they also react in a 1-to-1 molar ratio, at the end point, the molarity of the acid times the volume of the acid will equal the molarity of the base times the volume of the base. Only this time, the molarity of the acid, I don't know, because that's what I'm trying to find out. And I know how much I'm going to measure out. I'm going to measure out exactly 20 milliliters using a different pipette. And then from this algebra over here, from our first titration, we'll know this number. We'll know that number. We'll plug it in here, and then we'll know the new Buret reading for the second titration. And then we can find the molarity of the acid by dividing both sides by 20. And so we'll just do some algebra and get it done. So that's our purpose. We're going to ultimately prove that that is supposedly 5% acid. All right, so I've got to do my first titration. So I'm going to take my pipette, and I'm going to measure out exactly 20 milliliters of this exactly 1.0 molar HCl and put it in the flask. So, excuse me, here I go. We're going to take the acid and we'll pull it up with this suction bulb into the pipette.
Is that 1 molar?
It's exactly 1.0 molar.
And that's the
Hydrochloric acid. All right, I'll go past the line a little bit so that I can drop it back down and get the. I got to get that meniscus, the part where it came down. I got to get that exactly on that line. Just like in the burette, I've got the ammonia exactly on the 0 point. See, this reads from top to bottom, 0 down to 50, because I got to know how much I add. Okay, so now I've got the hydrochloric acid in the pipette, and I'm going to expel a little bit of it so that I get that exactly on that line. Then I'm going to put it in the flask. To do that, I can just take the bulb off and let it drain my gravity. Okay, so the hydrochloric acid is now going in the flask. And I measured exactly 20 milliliters of it, so I have now 20 times 1, which is exactly 20 millimoles of HCl in the flask. 20 millimoles in the flask. All right, so set that pipette aside. Now, you mustn't forget to add the indicator, because it's going to be colorless in that acid. So you only need a few drops of the indicator. And of course, it stays colorless. And by the time I add enough of the ammonia, according to this stoichiometry, to completely neutralize all that HCl, it'll stay more or less colorless. It'll start turning a little pink when the surfaces meet, but I've got to keep adding titrant until I get the first permanent pink color. Then I'll know that all the HCl has been titrated. When that happens, we call it the end point. And it's at that point that this math kicks in, that this times this equals that times that, and we can solve for that once we read this reading. Okay, so I've got the, oh, and by the way, I also have some distilled water. As I add this, if it happens to splash, I can rinse it down with water, and it won't change, it won't make any difference, because I've already measured how much acid this is. And distilled water will not change that. So I've already measured, it's okay, if I need to, it's okay to rinse it down a little bit. So here I go. I guess I should get down at this level, because I can't see what I'm doing. Standing way up here. So, I'm going to just add titrant. I have that exactly on 0. And so as I add it, I'm going to swirl the flask a little bit and let it mix. And then at my first permanent color of pink, I'm going to stop. And so this little faucet-looking device is called the Stopcock.
Stopcock.
S-T-O-P-C-O-C-K. I know, yeah, you're 14 years old and laughing at that word. Can you see it? It's foaming.
It looks white and cloudy.
Well, it's cloudy and white because it's foaming. It's foaming a little bit. Ammonia, I had a terrible time filling this up because when I add this, it foams. I don't know if you saw me, but I was sticking paper towel in there to make the bubbles go up the paper towel away from because I can't read a bubble, so I had to mess around with it. So here we go. We're adding it
Until it turns pink.
Yeah, if you were to come up closer, you could see that when it hits the surface, it turns a little bit pink and then it fades. So I'm going to do this until the first permanent pink color. I don't know, maybe you can see it from if you got eagle eyes, you can maybe see where it hits. Can you see it turning a little pink there by where it hits?
Mm-mm.
Barely.
Well, you're welcome to come up here and see it, but it does turn a little pink where it hits. I don't know, how much have I added so far? Okay, I don't know. We'll just wait until it turns pink, and then we'll finish it off. It's not really pink yet, do you think?
No.
I put a little white background here, so because the brown is a little hard to see through. I splashed something. I need to rinse it down a little bit. All right, so here we go. Adding more titrant. Okay.
It kind of looks baby pink.
Well, but it fades.
Yeah.
If it fades, then we got to add more.
Yeah.
It faded, right? Notice the pink is staying a little longer. That's because I am actually neutralizing millimoles upon millimoles of HCl with that ammonia because it acts as a base. And so as I do, it stays pink a little longer because until the HCl reaches it, it stays pink. Okay, so we'll continue until we get our first permanent pink color.
There we go.
Rinse it down a little bit, make sure I get it all.
Mm-mm.
Okay. I don't think so. I've added maybe what? About 18 milliliters so far. Okay. Okay, let's just add this till it stops, I guess.
Oh, it's kind of big.
Stays a little bit longer each time, doesn't it? Stays a little bit longer. But I think it went away again, didn't it?
No, it's still there.
Is it pinkish to you?
No.
Oh,
Not
that's
quite.
the reflection I get here.
Okay. It does stay a little longer, though. Can you tell?
Mm-hmm. Is it supposed to be hot pink, like that?
Well, because of the dilution with the other, it'll be light pink. You know, that's very kind of pure beige. So it'll only be slightly pink. And the first permanent pink is where I must stop.
Yeah.
Because if it stays permanently pink, it means all the acid's gone.
Is it titrated?
It's called titrated, yeah. And we're at the end point. And I've neutralized all the acid. And it stays pink at the excess base. Staying pink a little longer, but I think that's faded, is it?
Mm-hmm.
A little more.
Yeah.
Yes, don't.
You think?
Mm-hmm.
You think it's pink?
Mm-hmm. Looks like it's going away.
It's kind of pinkish, isn't it? Not really ferociously pink, but should we stop or not?
No.
We'll add a split drop and see if it makes a difference.
Yeah, that is right.
That's probably a good stopping place, don't you think?
Mm-hmm.
You know, if you have a question about a color, ask a female over a male, because males are colorblind, or can be, because it's a sex-linked problem.
Mm.
Women carry color blindness and pass it on to their sons, but not their daughters.
How much, what was in the,
There's ammonium hydroxide in the burette.
how much did we add?
Well, I have to read that now.
Oh.
And I have to get it up to eye level in order to read it. Because if I read it not at exactly eye level, then there's parallax and I'll make an error. So I have to read it, it's over 19 milliliters, so it looks like about, it looks to be like about 19.6 milliliters. I'm going to go with 19.6. Approximately. I can only guesstimate. So this is 19.6 milliliters of ammonia was added. Well, see, according to this then, if I put in 19.6 for this volume, and then algebraically solve for MB, the molarity of the base, then I should get it to be 1.0 times 20.0 over 19.6. Should be my, and the milliliters cancel the milliliters, and my answer will come out molarity, which is what I wanted to know. We want to know, as best as I can guess it, and measure it, I meant to say, the molarity of that household ammonia. So on my calculator, I could figure this out, I guess. We've got something like, well, we've got 20 divided by 19.6. 20 divided by 19.6 is about 1.02. Does that sound right? What about 1.02? That's molar. So that's faded again, though, hasn't it?
No.
No, it's still pink.
It's still pinky. It looks a little bit.
It looks pinker.
It's a little pinker, yeah. So we probably are close enough for college work. All right, now, what I'm going to do is, first of all, I'm going to put the volume on exactly the 20 milliliter mark, because I don't like dealing with the decimal. As my new starting point, I'm going to start at exactly 20 milliliters. That'll be my 0 point. I'm just going to, in other words, I'm just going to drain this down until it reaches exactly 20. And that's just my preference.
Do we need to put that in the lab?
No. You can just say we readjusted the level in the burette so that our initial volume reads exactly 20. So over here, when I find the volume of titrant added, it's going to equal the final volume that I get minus that initial volume, because I'm not starting at 0 anymore. Volume initial is going to be 20, is what I'm saying. And so whatever I read final on the burette after I titrate the ammonia versus the vinegar, then that final reading minus that initial 20 will be the actual burette reading of how much titrant I added, right? You know, like when you look at your car's odometer, when you start off and then you end the trip, the difference is how far you went. That's what I'm doing. I'm making a conveniently easy number to remember for my initial volume. So I'm giving that exactly on the 20 milliliter mark. All right, that's my initial volume. All right, so we'll keep that in mind. Now, of course, I'm going to take a clean pipette and another rubber bowl, and I'm going to pull up out of the vinegar bottle exactly 20 milliliters of the acetic acid that's in vinegar. And I've got another flask that I'm going to put it in. So we can put these two away. We're finished with the hydrochloric acid and the ammonia. And now here's my light distilled vinegar. I guess I had 20 milliliters in there, it looks like. And we'll pull up exactly 20 milliliters of that. If you had any fish, you could have fish and chips. Just pull that up. I use my finger to zero it this time. Okay. I want it exactly on that mark. When you see pictures of scientists doing this, you know, in the movies, and they're holding it up to eye level, they're not trying to look scientific. They're just making sure that their eye is level with what they're trying to read. Okay, so I'm going to put that in the flask. Okay, here we go. You know, there were days when I would do these titrations that I would make a setup. People would work in pairs, and I'd have a setup for everybody to do. And I don't have that right now, but back then, I mean, this one girl was titrating along. And she said, Dr. Miller, I've added like 49 milliliters, and this thing still hasn't turned pink. I said, did you add the phenolphthalein? Oh. You see, if you don't add the phenolphthalein, it ain't ever going to turn pink. Okay. So now I've added a few drops of phenolphthalein as my indicator, and I'm going to do exactly what I just did, only I'm starting at the 20 milliliter mark, and I'm going to see how much more I have to add. The difference between the initial reading and the final reading would be how much I actually added, right? And so here I go. Make sure this is level. Looks like I've got it crooked. There we go. I got a little crooked there messing with it. It is on the 20 milliliter mark. This is my flask. And now I've got a new titration going on. This time, we're taking the ammonia that we now know has a molarity of about 1.02. So now the only thing we don't know, and once we get this burette reading, the only thing we won't know is the molarity of that acid, which is what we're trying to find out. So because, see, I don't know this is 1.02, and molar, and I'll soon know this when I find the final reading and do this subtraction. I'll put that number here. I'll divide both sides by 20 and get the molarity of the acid. The molarity of the acid will equal whatever I get here times this number I don't know yet, but I will soon, and it'll be divided by 20 this time. And when I get done, this will be milliliters, and that's molarity. It'll come out with so many moles. And that would be the molarity of the base. I mean, sorry, the acid this time. Molarity of the acetic acid in vinegar. Then, like I say, we can do an assumption that the density of this weak solution is about the same as the density of water, which is not a bad assumption, really. That is, it's 1 gram per milliliter, and then we can turn our molarity into a percent and see how close we get. So here I go then. I'm going to lower the the burette a little bit so that it's down close to the opening of the flask. And then it's going to do what I just did. It's called titration. Titration is kind of neat because it shows you the uniformity of a solution. Not only is this acid in here exactly, or was 1 molar, but every drop of it is 1 molar. Did you see it only took like the next drop to have the excess and have destroyed all the acid? So it goes on almost like a light. That's how uniform a solution is. So remember, we call a solution a homogeneous mixture. And we mean by that it's uniform. Okay, so that's kind of interesting. So here we go. We're going to titrate this thing as best we can. So again, we're adding the titrant, which is ammonia, which we now know is probably about 1.02 molar. And we're titrating it this time against the acid and vinegar. And as you can see from where you're sitting, as they meet, it turns a little bit pink and then fades, right? Can you see that? What do you think? Not yet, huh?
Fade.
Oh, not yet. But I don't know if you can see from where you're sitting. You see how the foam turns a little pink and then fades? I don't know if you can see that, but... Still fairly colorless. I don't know where I am, but there we go. Not yet.
There, no.
It's staying a little pinker a little longer, isn't it? But I don't think I'm done yet. Let's it down a little. Yeah, that's what I've been saying. But it fades, right?
Yeah.
Getting closer, isn't it? You think? Not yet?
Got it faded.
Yeah. No?
It faded.
It faded. Did it fade?
It faded.
Beaker.
Oh, there it goes. It's not going to fade.
Think that's all right?
Yeah. We probably do a little more.
Is it permanent pink yet or not?
Yeah.
Permanent.
One more split drop, just to make sure, okay?
Okay.
Let's see. Whoops. Careful. Is that pink enough to stop, you reckon?
Yeah.
It's not as pink as this because I added extra, but it's pink, right? Well, then let's read it and see where we stand. We have added, if I can read this. Looks like, I really hate to say this, but that looks like exactly 36.5. The reason I hate to say it is people are prejudiced toward reading that half line, but no, it's right on that thing. 36.5. About 36.5, I would say. That's the final reading. I must always make sure. Let me get this thing perpendicular. Yeah, you don't want me to know. I need a dark background so I can, the light blinds me. There you go.
There's no hardly any left.
No, of course, we don't need any more though, we're done. It might actually be 0.6. So let's go with 0.6. How do you go? What is that, a difference of about 16.6? Would you say? Right?
Right.
I think that's right. That's what I got. 36.6 minus 20. 16.6, yeah? All right, now that's the number I'm going to put in here. Now, this many milliliters then, divided by that many milliliters and times that, should give me an approximation to the molarity of this acid that's in this vinegar. So I don't know, let's see what we get if we do that. Oh, 16.6 times about 1.02, and that divided by 20 gives me about 0.847. Let's call it 0.85. We don't need that many decimals, but we only had two significant figures to start with, so let's round it off to 0.85. About 0.85 molar. Now, here's where our assumption comes in. What is molarity? Molarity is moles of solute per liter of solution. Right? So when I say that I think that this vinegar is about 0.85 molar, I'm saying there's 0.85 moles of C20H14O4 in every 1 liter of solution. Well, if I knew the molar mass of acetic acid, I could multiply that times that, and I'd know how many grams there are in a liter. And if I make the assumption that the density is a gram per milliliter, then I know how many grams in 1,000 grams. And then grams over total grams times 100 will be percent. So I'm going to have to add up the molar mass of acetic acid. Well, that's 24, the 2 carbons. And then we got 4 total hydrogens, so that's 28. And 28 and 32, I believe, is 60. This 60 grams per mole. You know how to do that, right? 60 grams per mole. Make sure you add it up right. 24. I'm rounding off, of course. 24. 4 more is 28. And 2 16ths is 32. And 28 and 32 is in fact 60. Okay, just making sure. All right, so now let's do that. We now know then there's 0.85 of 60, there's this many moles, times this many grams per mole, over, let's call it 1,000 grams. This is a liter will weigh 1,000 grams if it is 1 gram per milliliter, because there's 1,000 milliliters in a, right? So this then, that fraction, that point, let me erase this here. That 0.85 times 60 over 1,000, and then that times 100 will be the percent. That's what we mean by percent. The total mass, the mass of the acid over the total mass times 100 is what we mean by percent. Pardon?
5.1, right?
I don't know yet. I haven't done it. But I can see that, that 100 will divide that 1,000 10 times, and then 10 goes into 66 times, and so my answer should be 0.85 of 6, whatever 0.85 of 6 is. Don't let my math fool you. Do it on your calculator, if you'd rather. 0.85 of 6. Well, that's 5.1 molar. Well, then that is 5 molar. I mean to say percent. That's 5.1%. The bottle is labeled 5%. Oops. And it's only given to one significant figure, and so to that one significant figure, we got exactly what it says on the bottle. That is 5%.
So it's proven right.
So there is truth in the labeling on this bottle. It is, in fact, 5%. Rounded off, 5.1 is 5%. And that's all they give you is one number. So that also, by the way, you should be impressed by the fact that we did something so accurately with, just a burette and a couple of pipettes. And titration is a very precise and nice little methodology. Yeah.
What's the thing holding the burette called?
Oh, that's called a burette clamp. And this is called a ring stand.
Okay, how do you spell burette? I don't
B-U-R-E-T.
B-U-R-E-T.
There's a fancier way to spell it with 2 T's and 2 E's, but I'm just using the simple Buret.
Okay, I'll make sure.
That's how they say it in Arkansas. It's a Buret. I hope I didn't offend anybody from Arkansas. Okay. We're done for the day. It's going to take me the rest of it. Oh, no. I can give you back your stuff.
And what was the purpose again?
Proof and labeling. They claimed this was 5%, and we proved it was 5%.
Oh, good.